Multiplying Probabilities, Lesson 15.6c. We're now up to 16 previous videos for this chapter. As I always say, if you become lost or confused, just click the description and find out which video you missed. We can find the probability that one event and another event will occur. When rolling a number cube, a die, the sample space S is 1, 2, 3, 4, 5, 6. There's 6 sides to the cube, so there's going to be 6 numbers. When flipping a coin, our sample space is just heads or tails. We can say H and T for heads and tails. But what if our experiment involved rolling a die and flipping a coin? Well, this would be a compound probability. The sample space for the experiment of rolling a number cube and flipping a coin is, we would have a 1 with a heads or a 1 with a tails, a 2 with a heads or a 2 with a tails, see, 3 with heads, 3 with tails, all the way down to 6. And the probability of any of these compound events occurring is the compound probability. So our sample space for rolling the number cube was the 1, 2, 3, 4, 5, 6, and for the coin it was heads or tails. Well, if A is the event a number cube comes up a 3, then our compound event would be a 3H or a 3T for 3 heads or 3 tails. If B is the event that the coin lands on heads, then we have our 1, 2, 3, 4, 5, 6 from our cube sample space and all heads. See? All right? And we can see the events are not mutually exclusive because A intersect B is 3H. So here we have a 3H, and here we have a 3H. So they're not mutually exclusive. And also, these events are independent of each other. The occurrence of event A has no effect on the occurrence of event B. Rolling that number cube has no effect on flipping that coin, does it? So they're independent. So what is the probability of A intersect B? Well, it's the same as asking what the probability is of flipping a 3 and a heads. This corresponds to the outcome, 3H. Because we have 12 possible outcomes, we have the probability of 3H as 1/12. We've got 6 elements here, we've got 2 here, and 6 times 2 is 12. And that means that this is one of the 12 possible outcomes. The probability of A is a half because we had a 3H or a 3T. So 3H is half of the outcomes, isn't it? There's 2 outcomes here. The 3H is half of the outcomes of these 2. The probability of B is 1/6. The 3H is one of 6 possible outcomes. See? We do the 1/2 times 1/6, and we get 1/12. So that brings us to our theorem. 2 events, A and B, are independent if and only if the probability of A intersect B is equal to the probability of A times the probability of B. Let's try it with marbles. A bag contains 3 red marbles and 5 blue marbles. A marble is picked, then put back into the bag. So that's very important that it's put back into the bag after it's picked. A second marble is picked. What's the probability of picking a blue marble both times? So we're going to let event A be that first marble that it is blue. And we're going to let event B be that the second marble is also blue. We have the probability of A is 5/8. There's 3 red, 5 blue, so there's 8 total marbles. And the chance that it's blue is going to be 5 out of 8. It's going to be 5/8. And the probability of B is going to be the same, 5/8, because we put that first marble back. And the events are independent because by replacing the marble, that first marble, into the bag means there's no effect on the second pick. So we can use our theorem. The probability of A intersect B equals the probability of A times the probability of B. We can do 5/8 times 5/8 and get 25/64. So the probability of a blue marble being picked both times is 25/64. See? Some events are independent. The outcome of a coin flip doesn't influence the next flip. The outcome of rolling a die doesn't influence the next roll. But if a card is picked from a deck and not put back, the outcome of the second card that's picked depends on the outcome of the first card. If we first pick an ace of hearts and we don't put it back, well, that ace of hearts is gone out of the deck. The second pick cannot be the ace of hearts. See, then it would depend on it. But if we put the card back, the second pick could be it, couldn't it? Then they would be independent of each other. So it depends on if you're putting it back or not, okay? A bag contains black, white, and blue poker chips. The probability of picking a black chip is 0.5. The probability of picking a white chip is 0.3, and the probability of picking a blue chip is 0.2. If one chip is picked at random, what's the probability that the chip will be white or blue? So the white one was 0.3 and the blue one was 0.2. These events are mutually exclusive of each other. So 0.3 plus 0.2 is equal to 0.5. If two chips are picked with replacement after the first pick, what's the probability that the chips are both black? Well, it said black chips were 0.5. So the probability of them both black, we would do 0.5 times 0.5 and get 0.25. See? A card is picked from a deck of 52 cards. What is the probability that the card will be a heart or a face card? There's 4 suits to each deck: hearts, diamonds, clubs, spades. If we do 52 cards divided by the 4 suits, that means there must be 13 hearts. If we take away the face cards out of the hearts, there's 3 of them, that means there's 10 heart cards that are not faces. There are 3 face cards for each suit, the jack, the queen, the king. So 4 suits times 3 face cards is 12 face cards. We do 10 50 seconds plus 12 50 seconds. That's going to give us 22 50 seconds or 11:26 when we simplify it. And what is the probability that the card will be a heart and a face card? So think about this. This is really simple if you think about it. For it to be a heart and a face card, there's 13 hearts but only 3 heart face cards. So that means there's only 3 out of the 52 cards that could be heart and face cards. So it would be 350 seconds. See? So just because you see the word and doesn't mean you're going to multiply right away. Have some common sense and think about it. It's just 3 out of the 52 cards can be hearts and face cards, couldn't they? All right? I hope this was clear enough for you. I know a lot of people get really confused when it comes to probabilities. We're going to talk about the complement of an event next, and we're going to talk about the notation for the complement, how you would write it, okay? That would be 15.6D. And don't forget, I've got the links in the description, and I hope you're doing well, and I'll see you next time. Bye.